This is our application challenge. I'm Joe Stradoff with Namir Burke and Ishan Sharma.
So for the problem, we chose to consider a car traveling on the highway at a constant speed, and our goal was to find the optimal speed at which the car should travel and minimize the fuel consumption. So for the simulation, we use MATLAB, which like to simulate the extreme seeking controller, and we initially had like a certain speed the car was moving at, and then we use the controller and alter the speed of the car to reduce fuel consumption. And the next one is the social and the environmental aspects or the impacts of the whole problem. So optimizing the speed of this vehicle to minimize the fuel consumption can result in decreasing greenhouse gas emissions and eventually decreasing the air pollution as they correlate, and which has really major positive effects on health as it will reduce the air, water, and all sorts of other pollutions. It can also encourage the use of alternate transportation, which are much more energy renewable, such as public transportation and biking or walking, etc. It can also help us become less reliant on foreign oil and boost our energy security. It can aid in fight against climate change, and as it can lessen the amount of oil extraction in the oceans. And it can also aid in keeping our transportation system sustainable over the long term. It can support greater economic justice by easing the impact of high gasoline prices on households with really low income. And the underlying physics to this problem was the internal combustion engine's conversion of fuel into mechanical energy, which is like governed by the laws of thermodynamics. The effectiveness of this procedure was influenced by variables including the combustion process, the temperature and pressure of the working fluid, and the engine's compression ratio. Another factor is the aerodynamics of the vehicle. In particular, it plays a crucial role in the optimization of the vehicle speed, as optimizing the shape and design of the vehicle can assist in minimizing the drag and increasing fuel efficiency eventually. The amount of drag that a vehicle experiences as it passes through the air can have a major impact on fuel consumption. Another optional factor we could consider are the environmental elements, including the weather, traffic patterns, and the road condition, which can also affect how a vehicle performs.
For the formula, we looked at the force on the car. There's the force of drag, rho CDAF x squared over 2, frictional force, mu mg, and we set the forces as an equation, and at constant speed the acceleration would equal 0, so we could zero out x dot, and then we get mu equals mu mg plus rho CDAF x squared over 2. And from this we can find the power, which is just mu 0 times x. Once we find the power, we can use Willen's line to find the conversion of fuel consumption to power, and that would be m dot f, which is in terms of time, so we have to divide it by x naught, so we get it in terms of distance. So we get m dot plus beta po, which is power, over x naught, which is m dot over xo plus beta u u naught. Once we find that, we could substitute u naught, and that would be the fuel consumption.
So for our extreme seeking controller, we implemented this in MATLAB. So we took the previous function and ported it over into MATLAB code, with the input being the speed and the output being the fuel consumption. and then we implemented the extreme seeking controller. Again, the important thing to note is that the frequency of the high pass filter is lower than that of the low pass filter, which is lower than that of the dither frequency. And in tuning this algorithm, we found that increasing the gain, which is the 10 over here, to a higher value gave us a faster response. And then our final result was around 35 meters per second speed, correlates to around 20 kilograms of fuel consumed per hour. And that 35 meters per second correlates to about 80 miles an hour, which is roughly highway speed.